Good day, my angels. Here is the solution to the momentum review. And make sure you check your email. Yesterday, I sent you some information about your momentum test. And yes, you read that right. For the momentum test, I'm going to give you 3 questions. For each question, I'm going to give you the answers. And your job is going to be to prove to me that the answer is correct. Basically, you should know ahead of time whether or not you've got perfect on the test. Okay? Also, I'm going to send out some information about test scores and rewrites and how that's going to work. I just still haven't quite figured that out yet, but I'll send that information out in a couple of days too. So, looking at the homework, here we go. Number 1 says, a person can survive a feet-first impact at a speed of about 12 meters per second on concrete, 15 meters per second on soil, and 34 meters per second on water. Why the different values for the different surfaces? So in each of these, we have a change in momentum, an impulse. And there's 2 ways to think about that. There's m times change in velocity, and there's force times change in time. So if I make the change in time larger as delta t increases, the force can decrease. And so that means that I can get away with having a bigger change in velocity. So that's why when we look at these different values, that's why we get a different change in velocity. Different change in time, bigger change in time, say for landing in water, takes it longer to bring you to a stop, lowers the impact force, and you have lets you have a bigger change in velocity. I think the way I said it in the answer key, I said concrete. You know what, Mr. Dewick, why don't you just look at the answer key? That's a good idea. I wrote, concrete will stop a person in much less time. Smaller t means much larger force. Okay? Number 2. When catching a foul ball at a baseball game, why is it important to extend your bare hands upwards so that they can move downwards as the ball is being caught? Why is it important to cushion the ball? You know what, Mr. Dewick? Trying to type this won't work very well. I'll just say this. As delta t increases, force decreases. Doesn't hurt as much. You don't have as big a force. Same if you're ever doing like a water balloon catch or catching an egg, if you're doing an egg toss. Again, you try and cushion it. Number 3. Automobiles were previously manufactured to be as rigid as possible, where now, today, they're designed to crumple upon impact. Why? Same kind of idea. It's all about increasing the time. Increasing the time lowers the impact force. And if you can lower the force, F equals ma, you're not changing the mass, you're reducing the acceleration. And we said a long time ago, it's acceleration that does damage during accidents, not force, not speed, it's the acceleration. Number 4, I ignored this, I crossed it out, but in terms of impulse and momentum, why is it important that helicopter blades deflect air downwards? Well, this is both a forces come in pairs, helicopter blades push downwards on the air pushes up on the blades, but it's also an impulse momentum question because the helicopter blades give the air downwards momentum because momentum is conserved. The air gives the helicopter blades upwards momentum. Number 5. A lunar vehicle is tested on Earth at a speed of 5 meters per second. When it travels just as fast on the moon, is its momentum on the moon more, less, or the same as? Well, momentum equals mass times velocity on the moon, same m, same v, so same momentum, same p. What changes on the moon? Your weight does, which is your mg, but there is no g in this equation, just m and v. Number 6. You may have seen large yellow containers on highways at exit ramps. In fact, there's some, I think, by the Pitt River Bridge. These containers are filled with sand or water. Newer containers have a loose top half resting on a bottom. These containers are designed to protect cars that would otherwise hit solid concrete barriers. How does physics explain how these containers, fancy word, impact attenuators, work? Well, again, we have the same idea. Increasing the time of impact lowers the force of impact. So it's all about impulse equals force times time. Number 7. A skateboarder has a mass of 90 kilograms. A car has a mass of 900. Explain how it's possible for them to both have the same momentum. Well, how about like this? If car goes 1 meter per second, then momentum equals mv, which is 900 times 1, which I can do in my head, 900 kilogram meters per second. If skateboard goes 10 meters per second, momentum equals 90 times 10, 900 kilogram meters per second. So if the skateboard goes basically 10 times faster than the car, basically as long as the skateboarder goes 10 times faster than the car, since the car has 10 times the mass. Next question, number 8. Why are the impulses that colliding objects exert on each other equal and opposite? I crossed that out, but it's a consequence of Newton's third, forces come in pairs. A boxer, I skipped number 9 as well. A boxer can punch a heavy bag for more than an hour without tiring, but will tire quickly when boxing with an opponent for a few minutes. Hint. Why? Hint. When the boxer's fist is aimed at the bag, what supplies the impulse to stop the punches? The bag does. When the boxer's fist is aimed at the opponent, what or who supplies the impulse to stop the punches that don't connect? The boxer does. So the reason boxing a person is so much more tiring than boxing a bag, when you're punching a bag, you never miss. And so the bag supplies the impulse to bring your fist to a stop. When you're punching a person, when you're boxing a person, you miss an awful lot. And so you have to apply the impulse to your own fist to bring your fist to a stop. So it's going to be much more tiring. Number 10, one of my favorites, just because I've seen it happen so often when I used to work at a summer camp. You are at the front of a floating canoe near a dock. You jump forwards, expecting to land on the dock easily. Instead, you land in the water. So, as you have momentum forwards, canoe must have momentum backwards, since momentum is conserved. And also, because the canoe probably has less mass than you, and momentum is mass times velocity, it's going to move backwards faster than you tried to jump forwards, and so it's going to slip out from underneath your feet, and you're going to do a lovely belly flop into the water. So, splash. Number 11. The classic physics problem. If a large bus and a small car have the same head-on collision, which will experience the greater force? The same forces come in pairs, which we called Newton's third. Which one will have the greater impulse? The same, since same force and same time. Which one will have the greater change in momentum? The same, since impulse equals change in momentum. They're interchangeable with each other. The greater acceleration. The small car, since it has a smaller mass. And that's why the small car, the people inside the small car, will experience greater damage, because what does the damage in an accident is not the force, it's the acceleration. Number 12, I skipped, but what's the object's change in momentum? 6 times 10, 60 Newton seconds, or kilogram meters per second. What's its change in velocity? Take that 60, divide it by the mass. The change in velocity would be 20. Number 13, this is a good example of what you might see on your test. A snow scooter has a mass of 250 kilograms. A constant force acts on it for 60 seconds. What change in momentum? So change in momentum, also called impulse. You know what? I think I'm going to use mv final minus mv initial, because I noticed they gave me a final velocity and an initial velocity. On your test, I'll probably include a change in direction. So one of these will be north, one of these will be south, or one of these will be forwards, one of these will be backwards, or one of these will be east, one of these will be west, or one of these will be left, one of these will be right. Here, it looks like they're both in the same direction, so I don't need to make one of them negative and one of them positive. It's going to be 250 times 28 minus 250 times 6. Oh, wrong button. 250 times 28 minus 250 times 6, and I get 5,500 kilogram meters per second. You could also say Newton seconds, but since I used mass and velocity, I'll use those for my units. B, what's the magnitude of the force? Well, if impulse equals force times time, or times change in time, force must equal impulse divided by time. Get the F by itself. So it's going to be 5,500 divided by 60. .7 newtons. And they just wanted the magnitude, so I don't care about the direction. Next one, number 14. Nope, I skipped number 14. Number 15. Car weighing 15,680 newtons. First of all, please note that that's the weight. Okay. The mass is going to be the weight divided by g. It's going to be 15,680 divided by 9.8. And I get 1,600 kilograms. B. What's its initial momentum? I don't need was going to draw a delta, but I don't need to. This is not a change in momentum. The initial momentum is going to be mass times the initial velocity, which is going to be 1600 times 20. I could have done that in my head. 32,000 kilogram meters per second. C. What changes? So change in momentum is going to be, I don't think I'm going to use force times time. They gave me the force, but I notice in D they're asking me for the time. I'm going to use mv final minus mv initial. Let me just pause the video for a second. Sorry, got interrupted there, but I'm back. You know, although I could go mass times velocity, I know the final momentum. It says it's coming to a stop. So the final momentum is 0. And I know the initial momentum. I just calculated it in B. And I can do that in my head. Negative 32,000 kilogram meters per second. So what does that mean? That means that we've lost 32,000 kilogram meters per second of momentum. Well, of course we lost momentum. We had to come to a stop. By the way, instead of asking what change in momentum, I could also have just said, what is the impulse? Because that means the same thing. D, how long? Okay, now you're asking me to find a time. So I just figured out the impulse. So I think I can go impulse, or change in momentum, is force times time. So the time is going to be the impulse divided by the force. It's going to be negative 32,000 divided by, now the force that they gave me is 640 newtons, and you might say, Mr. Dewick, this is going to give me a negative time, and you said that time was a scalar, but the force is in the opposite direction that the car is traveling. How do I know that? Because it's slowing the car down, and so the force would be negative as well, in the same direction as the impulse. This should work out evenly. I think it will. 32,000. The negatives are going to cancel. Yeah, 50 seconds. So this was a nice, leisurely, take your time, slowing down to a stop, not a quick stop. And that's why the force was so small. 640 newtons, that's a pretty small force. What number was that? 15? 16. Oh, wrong button. A car of mass 11,000 moves at 22 meters per second. What braking force is needed to bring the car to a halt? Here, I'm going to combine the two impulse equations. I'm going to say force times the change in time equals mv final minus mv initial. Impulse equals impulse. mv final is 0 because it's coming to a halt or a stop. They want me to find the force. I'm just going to go divide by t, and I get force equals negative mv initial divided by time. Negative 1,100 times 22 divided by 20. What does the negative mean, Mr. Dewick? The negative means the force has to be in the opposite direction that the car is traveling in order to bring it to a stop. Oh, yeah, that makes sense. Number 17. When a bat hits a baseball, the change in momentum is, you know what? It's equal to, because momentum is conserved. Whatever momentum the bat loses, the baseball gains. Number 18. When a, continuation of the same question. I should have copied both of them. when a bat hits a baseball, the change in velocity of the bat is, okay, because the bat has more mass, so let's write this down. Bat and ball have same impulse, but bat has more mass, so smaller. Where's my delta symbol, Mr. Dewick? Do I have it here? Insert. Symbol. Show me a delta. I have to pause while I find out how to do a delta. There's the delta. So it's going to have a smaller change in velocity. So the answer is less than. The baseball is going to have a bigger change in velocity, which is why the baseball takes off like a rocket. Number 19. I like number 19. I like number 19. Number 19 is a nice question. They want the final speed and direction. I see a force. I see the time. Again, I'm going to use the idea that I can combine both of the impulse equations. They want me to get the V final by itself. So I'm going to get this. First thing I'll do is I'll plus the negative mv initial over to this side. I'll get force times time plus mv initial equals mv final. And then I guess I'll divide by m. Now I have to be really careful. I see west, I see east. I'm going to let east be positive, and west be negative. So I'm going to get this V final equals force times time, and force is a vector, plus mv initial, and that's a vector, divided by m. The force is positive, 0.07, plus 3.2, negative 4, all divided by 0.07. Is this a fraction? Brackets around the top. Divided by, don't need brackets around the bottom. Oh, I got the wrong mass there, Mr. Dewick. That's silly. 3.2. You were all screaming at me on YouTube there, weren't you? Caught myself, though. And I get 1.47, let's say. Meters per second. I got a positive answer, so if you want me to assign a direction to it, got to be east. If I got a negative answer, that would have been west. Number 20. Oh, we skipped number 20. Number 21. I like number 21. I like number 21. Number 21 is a nice question. A couple of things I don't like about it. Grams. Nice try, Mr. Dewick. 0.055 kilograms. The fact that we rebound means there's a change in direction. So I'm going to let one way be positive and one way be negative. I'll let the rebound be positive because I'm kind of imagining the pinball is rebounding it up-ish. And I'll let that be negative as though it's falling towards the pinball bumper. Down, towards. And they want me to find the force. So again, I'm going to use that combined question, the combined equation, impulse equals impulse. Getting messier and messier and messier. They want me to find the force. The force, this is also a vector, I keep forgetting to put the vector sign above the F, is going to be mv final minus mv initial all over t. Mr. Dewick, why did you put the vector sign above the F? It's just to remind myself, if I get a positive answer, then that's going to be that direction. If I get a negative force, that's going to be in that direction. it's going to be m 0.055 times 0.75 minus 0.055 times negative 0.6 all over 0.12. .055 times 0.75 minus 0.055 times negative 0.6 divided by 0.12. And I get 0.618, 0.62. 0.62 newtons. If they just wanted the magnitude, direction would be, it looks like in the direction of the final rebound, because I got a positive answer. .22. Okay, now we're getting into collisions, these next few questions. These are conservation of momentum questions. This is an inelastic collision. Inelastic means they stuck together. I'm going to call this mass A. I'm going to call this mass B for bullet. Before the collision, what's moving? Well, first of all, because there's a collision, the sum of all the initial momentum equals the sum of all the final momentum. Momentum is conserved.
Mr. Herman, would you mind stopping by the office, please? Brody Herman?
There you go. A little announcement for you over my shoulder. Before the collision, what's moving? Well, the cart and sandbag is at rest, so I'm just going to have the mass of the bullet, velocity of the bullet initial. And when they collide, they stick together, so it's going to be mass A plus mass B, V final. I like this question. I like this question. I like this question. You want me to get V final by itself? So I'm going to divide by the bracket. V final is going to be mass bullet, V bullet initial, divided by mass A plus mass B. Mass of the bullet, 0.002, because it's grams, so that's 0.002 kilograms. 550 meters per second. 4.5 plus 0.002. And I get 0.244 meters per second. They said velocity. I don't see a directional component here at all, so forwards in the same direction as the bullet. On a test, I would give you a clear direction in this question. So there's an example of a collision where the objects stick together. .23. Two boys of mass 45, you know what? I'll call this mass A, I'll call this mass B, are sitting on two separate 15-kilogram wagon. Oh, sorry. That's not mass A and B. That's mass A, that's mass B. Facing each other and holding a rope taut between them. The lighter boy pulls on the rope and acquires a velocity of 20 meters per second west. What is the velocity of the other boy? So before we start, we know that momentum is conserved. The total momentum we start with has to equal the total momentum we finish with. And the total momentum we're starting with is 0 because they're sitting. Afterwards, I'm going to have mass A VA plus mass B VB. Afterwards, they're both moving. They want me to get the velocity of the other boy, which I called mass B. They want me to get this by itself. First, I'm going to move this over. I'll get negative mass A VA equals mass B VB. And then to get the VB by itself, looks like I'll divide by mass B. I'll get VB equals the opposite direction of mass A, VA, all over mass B, negative, what was mass A? 60. V was 2. Now, west I'm calling right now positive, divided by 75, negative 60 times 2 divided by 75. I get negative 1.6 meters per second. If I called west positive, that's going to be 1.6 meters per second east. Number 24, ooh, train crash. Alrighty. What is the momentum of the heavier car? Well, the momentum of the heavier car, let's see. I'll call this H for heavy, and I'll call this one L for light, since that's the terminology they're using. The momentum of the heavier car is going to be the mass of the heavier car, velocity of the heavier car. It's going to be 113,000 times 1.2. And I get 135,600 kilogram meters per second. Now they're approaching each other, so I'm going to call this second velocity negative in the opposite direction. So when it wants me to find the momentum of the lighter car, that's going to be the mass of the lighter car times the velocity of the lighter car, and that's going to be 75,000 times negative 2.3. And I get negative 172,500. What's the velocity of the cars after the collision? It's inelastic, so they stick together. Okay. The total momentum we start with has to equal the total momentum we finish with. Before the collision, we have mass of the heavier car, velocity of the heavier car, plus mass of the lighter car, velocity of the lighter car, and when they collide, they stick together. I'll call that V final or V both or something like that. So the final velocity is going to be mhvh plus mlvl divided by mh plus ml. It's going to be 135,000, what did I say, 135,600? Since I already crunched it, plus negative 172,500 divided by 113,000 plus 75,000. Brackets around the top. And I get a negative answer, which means the lighter train wins, I guess. They almost cancel out. I almost get a velocity of 0, so this wreckage is barely moving after the crash. Negative 1.96, sorry, negative 0.196 meters per second. If they had given me directions like east or west, I could tell you whether this was east or west or whatever. I'll have to add some directions for next year. Child's ball. Of mass 560 grams. Nice try. 0.560 kilograms. Okay, they don't stick together. At least the question doesn't say so. So I'm going to start up by saying there's a collision, so I can say that momentum is conserved. I'll call this mass A. I'll call this mass B. So before the collision, what's moving? Mass A, velocity A initial. The bowling ball is not moving. Wham, they collide. They're both moving afterwards, and they're separate. And I guess they want me to get that by itself. First, I'll subtract this over to that side. I'll get mass A, V, A initial takeaway, mass B, V, B final. And then I'm going to divide by the mass of A. And that should give me VA final. So it's going to be 0.560 times 7.6, and I'll call east positive, minus 4.5 times 1.5, all divided by 0.560. Making sure I didn't make any typos. And I get a negative answer. So negative means what? West. I guess the bowling ball got pushed forwards, but the small ball bounced backwards. I get VA final equals negative 4.45, which is 4.45 meters per second west. Another train question. Mr. Dewick, you must not like trains. Yeah. So in this collision, they don't stick together. They bounce apart. It's elastic. And the lighter one bounces backwards off the train. Now, how realistic is that? I realize they'd probably just smoosh and stick together, but humor me. There is a collision. The sum of all the momentum we start with equals the sum of all the momentum we finish with. I'll call this mass A. I'll call this positive. I'll call this mass B. I'll call this negative because they're head on. So before the collision, I have mass A, velocity A initial, mass B, velocity B initial. They collide. Afterwards, I have mass A, velocity A final, and mass B, velocity B final. They want me to find the velocity of the heavier car, that one there. So I think first I'll subtract this over. The left-hand side drops down like a domino. minus mass A, V, A final. And then I guess to get the V by itself, I would divide by the mass of B. That's going to give me V, B final all by itself. And now it's plug and chug. Complicated plug and chug, but it is plug and chug. It's going to be 76,000 times 3.5. 76,000 times 3.5. And then there is a plus 95,000 times negative 1.9 minus, I should be careful here. Since it reversed its direction, this one here is negative as well. The 0.42 is negative. So 76,000 times negative 0.42 all divided by 95,000. Calculator time, brackets around the top. So bracket 76,000 times 3.5 plus 95,000 times negative 1.9 minus 76,000 times negative 0.42, close off the top, divided by 95,000. And I get positive 1.236. I'll call it 1.24. Did I give east and west directions, or did I just say opposite directions? So if I'd given you directions, it's in the same direction as the lighter car. Opposite direction from the heavier car's initial velocity. The heavier car reverse direction and bounce backwards. Number 27. Continuing on, number 27. Two more, we're done. We have a collision. So this is a job for conservation of momentum. I'll call this mass A. I'll call this mass B. They're in the same direction, so just to make my life easy, I'll call everything positive. Are you sure, Mr. Newick? Yes, I'm positive. Okay. The sum of all the momentum we start with has to equal the sum of all the momentum we finished with. Before the collision, it looks like they're both moving. So I'm going to have the mass of car A, velocity of car A initial, and the mass of car B, velocity of car B initial. They collide, and I don't think they stick together because they gave me the speed of the smaller one. They want me to find the speed of the larger one. If they stuck together, that would be the answer. So I'm going to have mass AVA final plus mass BVB final. I like this question. I like this question. I like this question. They want me to find the speed of the larger car. The larger car is mass A after the collision, so they want me to get the VA final by itself. First, I'll subtract this over to that side. I'll get mass AVA initial plus mass BVB initial minus mass BVB final. And then I think I would divide by the mass of A, and that would give me the velocity of A final all by itself. Now it's plug and chug. 1,500, 15.6 plus 1,020, 12.5 minus Smaller car, 1020, 15.3. So the smaller car got a bump faster. It sped up. I think the bigger car is going to slow down, so I'm expecting an answer smaller than 15.6, all divided by the bigger car. Brackets around the top. 1,500 times 15.6 plus 1,020 times 12.5 minus 1,020 times 15.3, close off the top, divided by 1,500, and I get 13.7, let's call that. And I think the direction, since I got a positive answer and east was positive in my question. Last one. I like number 28. I like number 28. I like number 28 because explosions are cool when you're not around them. So for a recoil velocity, I'm going to use, how about R for rifle and B for bullet. Explosions are also governed by the law of conservation of momentum. Before we pull the trigger, what's moving? Nothing. So my initial momentum, I'll change colors, my initial momentum is 0. After I pull the trigger, I'm going to have the mass of the rifle, velocity of the rifle, and mass of the bullet, velocity of the bullet. They're going to end up going in opposite directions, so I'll let the bullet be positive. Yes, I'm positive. They want me to find the recoil velocity of the rifle. They want me to get that by itself. I think first I'll minus this over to that side. So I'll get negative mass bullet v bullet, and then I think I would divide by mass rifle. That'll get the velocity of the rifle by itself. It's going to be negative 0.036 times 290 divided by 3.2. And I get negative 3.26 meters per second. In other words, in the opposite direction of the bullet. If I had included easts and wests here, then we would have a directional component. So there you go. That's the review. Let me know if you still have questions, and I'll email out a version of the test. 3 questions. One question will be force and impulse and time question, and then 2 of the questions will involve collisions or explosions. One will be an inelastic collision where they stick together, and one will be an elastic collision or explosion where they come apart.